This is a continuation of the progression and the development of the unit circle, and we're going to look now at how the cast rule comes into play. So we looked at the last video about a rotation of a point around a circle when, or around about the origin, when the point was connected to the origin 1 unit away. And so we had what's called a terminal arm, and the terminal arm went through some sort of rotation starting at the positive x-axis. So from here, again, we've dropped this perpendicular here, so we've got our x values, the x distance towards this point, and we've got this y distance, and then we've got this radius. So when we look at the sine, cosine, and tangent ratios in the first quadrant, again, just looking at these ratios, we got sine theta equals y over r, which is opposite over hypotenuse. Cosine theta is x over r, which is adjacent over hypotenuse, and the tangent of theta is y over x, which is opposite over adjacent. I'll keep them in this form just for now, even though from before the unit circle this radius is 1, so we don't really need anything in the denominator here. We could just leave that out because the r is 1. However, just to illustrate this, when we look at the coordinates xy of this point here, we notice that the x coordinates being to the right of the y-axis, they're all going to be positive, and the y coordinate is going to be this distance here, which is above the x-axis, which means it's positive as well. And the radius, well, that's always going to be positive, and it's sort of intuitive that a radius will always be positive because it doesn't really make sense to have a negative radius. We can't go from, well, whatever point of rotation we start from, there's always going to be some sort of distance from it. It's kind of hard to go a negative distance per se. It would be in the opposite direction, I see, but it's not necessarily considered negative because it's the distance from the origin, or from the center of the circle to the circumference of the circle, as we were to rotate this about the circle there, or about the origin. So another way of looking at it, just to verify that that will be always positive, we know this is a right triangle, and I will there's another video on Pythagorean Theorem that you're more than welcome to view. So we have, I'm just going to copy this triangle down here, and it's a right triangle. So this brilliant man named Pythagoras came up with this theorem that if we were to draw squares off the sides of, and that's not drawn very well, off the sides of a right triangle, then if we were to look at the areas of each of those squares, and I'll try to get it as precise as possible, but it won't be perfect, of course. So if we have the areas of these squares, they always use A, B, and C to label them. So they got A, B, and C. So the two legs are labeled A and B. Sorry about that. A and B, and the hypotenuse is always labeled C. So what they would do then is they say, well, if this side length is A of the triangle, and maybe I'll highlight that in a different color to make it sort of stand out. So here's the triangle with side lengths A, B, and C. Well, if we know that the side lengths are the sides of a square, and we know squares have all sides that are equal, then the area of this would be a squared. And then this square up here, this area would be b squared. And then this side over here would form the triangle or the square that has the area of c squared. Well, I'm not a big fan of the a, b, and c thing. I would prefer to use L for the longest side, S for the shortest side, and M for the medium side. So this area down here is S squared, this is M squared, and this is L squared. So the largest square is equal to, so the area of the largest square is equal to the area of the smallest square plus the area of the medium square. And there are great videos online to demonstrate this using a wheel, and as they rotate it, the liquid would pour from the largest square into the two other squares here. But when we look at this formula, no matter where this terminal arm is, and we're going to look at it in the other three quadrants as well, but no matter where it is, when we square a number, we're going to get a positive number. And then, and I'll just highlight that in a different color as well. And when we square a second number, it's also going to be positive. So we're adding two positive numbers, so the result is going to be positive. And then when we take the square root of this, so we got L squared is that. So the square root of both sides, we get then L is then, of course, when you take the square root of a positive number, it's going to be a positive value. So that just shows you that the radius of our unit circle is always going to be positive. Okay, so when you go back up here, we've got, in this case for sine theta, a positive over an always positive. So that's going to be positive. Cosine is a positive over an always positive, so that's going to give you a positive. And then tangent, well, tangent is y and x, or sine and cosine. And because those are both positive, and we can see here to the right of the y-axis and above the x-axis, those are both going to be positive, so that means that tangent is going to be positive. So that tells us that all three of the trigonometric ratios for angles in the first quadrant will be positive. If we continue rotating this terminal arm around into the second quadrant, what happens then is that, well, the angle of rotation now is from the positive x-axis to here, so that's angle theta now. We've done with this one. And again, same sort of thing, we drop this perpendicular. We've got x on this side over here, y here, and r is over here. Well, in this case, sine theta, of course, again, y over r. Well, this y distance is, again, above the x-axis, so that's going to be y over r, which is going to be positive, because y is positive in this case, r is always positive, so that's going to really result in a positive sine ratio. Cosine of theta, where this theta is rotated around into the second quadrant, well, this x distance in this case is to the left of the y-axis, therefore the x value is actually negative. So a negative over an always positive is going to be negative. And then for tangent, again, same sort of thing as y over x, and the y is, of course, positive in this quadrant, but it's over x, which is negative, so when you divide a positive by a negative, you get a negative. So in this case, we see that only the sine ratio is positive for angles that have rotated into the second quadrant, so then, therefore, this is where sine is positive. We now continue the rotation. We're finished with this guy. We're going to rotate now from the positive x-axis around into the third quadrant. and we'll again drop the perpendicular. Well, this is the same side, this x is the same side as was in when the terminal arm was in the second quadrant. The y is now down here, and of course that's still r, still the radius. And we'll go through the same process again. So sine theta, sine, so now the angle of rotation is all the way around to here. So now that's the angle of rotation all the way around into the third quadrant. And so the angle of rotation there, the trigonometric ratio then for sine theta is going to be again opposite of our hypotenuse. This time y is below the x-axis, so y is going to be a negative, which is a negative over an always positive is going to give you a negative. And then cosine theta, again x is negative over the radius, which is positive, that's going to still be a negative. And then the tangent theta, well, now we've got y over x. Y is below the x-axis, which is the negative y values. X is to the right of the to the left of the y-axis, which is also the negative x values. So y over x is going to give you a negative over a negative, which is a positive. So now in this case, of the three trigonometric ratios, only tangent's positive. So that's why we're going to say that we're going to indicate that tangent is positive down in this quadrant. And then when we look over here into the fourth quadrant, we're finished with this angle here, and we're going to rotate this down here, drop the perpendicular, and the angle then is, I'll go on the inside now, this angle is rotated from the positive x-axis all the way around into the fourth quadrant, so that's angle theta now. Again, we've got the x here, the y here, and the radius is here. So sine theta, again, y over r, and y is negative because it's in a position below the x-axis. Y is negative over the positive r, which gives you a negative. Cosine theta, well, the x, because it's adjacent over hypotenuse, the x is positive, it's to the positive side of the y-axis, so that x over r is going to be positive because, of course, radius is always positive. And then the tangent theta is y over x. Y is negative over the positive x, and that gives you a negative. So in this case, only cosine is positive, so therefore in this quadrant we say that cosine is going to be positive. So when we look at where the terminal arm would have been rotated about the origin, starting from the x-axis, into which quadrant the terminal arm may end up or stop, we would then take a look. This is called then the cast rule, because we see that when the terminal arm is in this fourth quadrant, cosine is positive. This isn't called the cosine quadrant. This is just the fourth quadrant. If the terminal arm ends up in it, cosine is positive there. If the terminal arm is rotating from the positive x-axis and stops in the first quadrant, then all three of the trigonometric ratios are positive. If the terminal arm rotates into the second quadrant, that's where only sine is positive. And if the terminal arm rotates and stops in the third quadrant, that's where tangent is positive and the others are negative. Okay, so this just tells you, the cast rule just tells you where in which quadrant the different trigonometric ratios are positive. If they're not these ratios, so the cosine here, the sine in the second quadrant, the tangent in the third quadrant, then that means that the other two trigonometric ratios in each of those quadrants would be negative. Okay, so that is the development of the cast rule. And I guess I should have, now thinking back on this, I should have put the little positive for y over r, positive for x over r, positive for y over r or x. So then when you divide the positives, you get the positive for each of those. Here y is positive over positive, which leaves you the positive. X now is negative over positive, which gives you the negative. And tangent is positive over the negative x, which gives you the negative. Sine here is negative over the positive, giving you the negative. Cosine is negative over positive, giving you the negative. And then tangent is going to be the, negative over negative, so the double negatives here, which give you a positive there. And then in the last quadrant, sine is negative over the positive radius, giving you a negative. Cosine is positive over the positive radius, gives you the positive. And then for tangent, we got a negative over positive, which results in a negative. So that is how we have developed the cast rule.